Stuart Spath is the GRAIL Chief Space Systems Engineer, and he's going to talk to us about the spacecraft itself. So the instruments that Dr. Zuber described and the measurements, how do those all fit together in a spacecraft? Stuart joined Lockheed Martin in 1989, working on NASA's Magellan Venus orbiter mission as a test engineer. His next assignment was as the Attitude Control Subsystem Engineer for NASA's Mars Global Surveyor. He then became the chief of the mission's operations spacecraft team and supported 3 missions, the Global Surveyor, Mars Odyssey, and the Stardust mission. In 2001, he was named the Mission Operations Development Manager for the Spitzer Space Telescope, and he was selected as the Chief Systems Engineer in 2007 for GRAIL, and has been working since then on the design and development of the twin lunar orbiters. Please welcome Mr. Stuart Spath.
Thank you, Greg. It is a pleasure to be with you this afternoon. I personally have been working on the GRAIL mission for the better part of 5 years now, so it's a nail-biting time for me. I have a lot of blood, sweat, and tears into this point, and it'll be quite a relief to see this thing succeed tomorrow with weather permitting, of course. So next slide. All right, so this is the interactive portion of the presentation, so I'm going to need volunteers in the audience to shout out answers as we go along here. Mirror, mirror on the wall is my first category. You've heard about the twin spacecraft and so forth. Are they identical twins?
No.
One click, please. Almost. Those with very sharp eyes can see in this image here. This was taken in our frontal back chamber. The circled components are our star trackers, and if you look at the one on the left, which is GRAIL A, you can see that it's canted, tilted to the left, and the one on the right tilted to the right. The reason for that is when we're in lunar orbit, we want this star trackers canted away from the surface of the planet so that we don't get lunar albedo or reflections off the surface of the moon, therefore interrupting our ability to track the stars with the star trackers. You heard Maria talk about the moon cam cameras. Those are also minor differences between GRAIL A and GRAIL B. They're oriented in a way such that each one will get good views for the middle school kids and so forth. So very similar spacecraft, but not quite identical. All right, next one. All right, I call this size doesn't matter. How much does the GRAIL spacecraft weigh? Any guesses in pounds?
400.
400? Not bad. Click. About 677 pounds, and by spacecraft standards, that quite frankly is a midget. Very small, but the reason we do that is because the nature of the measurements that Maria was describing requires a very stable, very stiff platform. So the spacecraft have to be small, they have to be stiff, and they can't warp and so forth as they get thermal variation. So the size is important to be as small and compact as possible. By comparison, next click, Juno, which just launched to Jupiter last month, weighed a whopping 8,000 pounds. So we call this the David and Goliath of the industry. Next. All right, I call this next one plenty of room, and that's because if you look at the 2 GRAIL spacecraft in the fairing, there is plenty of room. In fact, you could almost envision 2 more or 4 more inside that fairing. Luckily, we don't need 2 more or 4 more. We've got all we need there. Next clip, please. Yeah, they, as you heard from Maria, they do sit side by side in the launch vehicle, and they're in the 10-foot fairing, and then they get released, GRAIL A first, and then about 8 minutes later, GRAIL B. They fly independently to the moon and insert themselves in lunar orbit on New Year's Eve and New Year's Day, respectively. Next. All right, power play. How much power is generated by the solar rays in watts? Any guesses? 40. That's ambitious. Next click. About 750 watts. And for those of you that are keeping track, that's about half of what it takes to power a modern-day hairdryer, which I don't use, by the way. But I read that on Google, so I'm going to read this correct. So both spacecraft together are basically have as much power as a hairdryer. That's not much power, and the reason we do that, of course, is power is money in space as is mass. So certainly one of our challenges with the spacecraft design is to keep the components low power, efficient, and so forth. Next clip, please. Obviously, during the mission, we're not always in view of the sun. We do go behind the moon and get occulted from the sun. So during those periods, we have a lithium-ion battery that powers the spacecraft during non-sunlit periods. Next. All right, I call this section, it's cold in space. How do we keep the spacecraft warm in the frigid environs of deep space, the vacuum? Anyone? Yeah, heaters. Next clip. So each spacecraft, even though they're small, have 101 different temperature sensors which control 158 different heaters. And that's all done autonomously. So the software is smart enough to monitor temperature sensors on various different components, various areas of the spacecraft, and then turn on or off the heaters as necessary to keep all the components within their operating ranges. So it's a complicated system, but it keeps us in the right operating range thermally for each of the instruments. Also on the right, you'll notice the gold foil. We call that multi-layer insulation. And much like you would put insulation in your attic, we put that around the main bus of the spacecraft, and that keeps the heat in. The computer and all the high-power components within the spacecraft generate a fair amount of heat inside, and by blanketing the exterior of the spacecraft, we're able to take advantage of that heat for the interior of the spacecraft. Next. Gas mileage. How much fuel does each spacecraft carry? And this is an old early photo during the propulsion integration. You can see right in the middle in the circle is our fuel tank. So in gallons, anyone want to take a guess at how much fuel we carry? 5,000 gallons? Not quite that much. Next click. About 29 gallons, and that's about the size of a large SUV. We do cost a little more than a large SUV, but I think we're going to get our money's worth out of this. And it does take about 1 gallon to get to the moon. So during the cruise phase, you saw the video that Maria showed, it takes about 1 gallon to get there en route. Of course, the ULA guys will take some credit for that, but 1 gallon on the way there, and then about 7 gallons to capture in the lunar orbit. And then we spend the rest of the fuel circularizing and getting into our final formation. It's hydrazine, which is not all that different from kerosene or something like that. Next. All right, I call this a bird's eye view, and those that were paying close attention to Maria's presentation, she gave the answer. How far above the lunar surface do we fly? 55 kilometers. Next, which is about, quick please, about 33 miles, and that's about 120 Cirrus towers. Next click. Yeah, so stack those on top of themselves 120 times. That's about how high these spacecraft are above the lunar surface. Next. All right, miles apart. How many miles apart are the two spacecraft? Maria gave it in kilometers, so you guys have to convert. Next click. About 100 miles. And so if you click one more time, please. We're right here at point A at KSC. If you took a nice leisurely drive up the coast when you came to St. Augustine, that'd be about how far the two spacecraft are apart. So quite a distance. And finally, next slide, I call this splitting hairs. How accurately can we measure the range? Again, Maria talked about how precise these measurements have to be. And even though we're 100 miles apart, we can measure with errors less than 15 microns, and even less, as Maria said, and so it's less than the width of a human hair. So, you know, that's pretty amazing to be that far away and still measuring within accuracies like that. So, next slide, please. On behalf of Lockheed Martin, we're privileged and proud to be part of this mission. We've had over 200 people contribute to the GRAIL mission, and it's our honor to be here today on this culminating occasion. So go GRAIL to the moon.